You know those online quizzes, right? The ones telling you your personality type or which, I don't know, superhero you are.
Mm.
Ever stop and think, is this actually measuring anything real?
Yeah, you do wonder.
Okay, now imagine something much more serious, like a professional licensing exam.
Mm.
You'd really want to know that test is accurately checking the right skills and knowledge.
Absolutely. The stakes are way higher.
And that's pretty much what we're diving into today, the whole idea of psychological test adequacy. Are these tools, consistently measuring what they're supposed to measure? It's crucial stuff if you ever encounter these kinds of assessments.
It really is. And our source material for this deep dive focuses on EPPP test construction. Now, okay, that's one specific exam,
Right.
but the core principles, we're hitting reliability and validity. These apply broadly. They're the bedrock for understanding if any psychological test is actually any good. Sort of the basic quality standards.
Exactly. So our mission today is to give you a clearer picture of these big ideas, hopefully some aha moments, without getting totally bogged down. We're kind of offering a shortcut to feeling informed.
Sounds good.
And just for context, there are a couple of big theories here. We're mainly drawing from classical test theory. It's the older one, focuses mostly on the overall test score.
Right.
There's also item response theory, which gets more into individual questions. It's interesting stuff, but for today, classical test theory gives us the main framework for reliability and validity. If IRT sounds cool, definitely check it out more later.
Good framing. So let's nail down the basics. What is a test in this context?
Good question.
Well, the formal definition is a systematic procedure for measuring a sample of an individual's behavior. Let's unpack systematic. First, the content has to be systematic.
Meaning not just random questions thrown together.
Exactly. They're carefully picked to represent the specific thing you're interested in measuring. Like that EPPP material, it's not testing random trivia. It's focused on core psychology knowledge.
Okay, systematic content. What else?
The administration is systematic. Standardized procedures, specific guidelines, things like time limits, instructions, the environment.
Ah, so everyone takes it under similar conditions. Fair playing field.
That's the goal, yeah.
Yeah.
Minimizes outside factors messing with the score. And third, the scoring is systematic. Clear rules, predetermined steps, cuts down on subjective judgment.
Okay, systematic content, administration, scoring. Got it. What about the sample of behavior part?
Right, that's key. Tests don't measure everything. They take a sample. The EPPP samples your psych knowledge. You can't possibly test every single fact.
Which, immediately raises a couple of potential problems, doesn't it? If you're only looking at a sample.
Absolutely. Two big ones. First is validity. Does the test actually measure what it claims to measure? Is it accurate? Like the Beck Depression Inventory, does it really tap into depression? That's validity.
Okay, validity hitting the target. Are we measuring the right thing? What's the second problem?
That's reliability. It's about consistency. If you took the test again tomorrow, or got a slightly different batch of questions on the same topic, would your score be similar?
Okay. Like a wonky bathroom scale. 7 it 3 times, get 3 different numbers. You don't trust it.
Exactly that. If someone scores low on a psych test, we need to be confident it reflects their actual knowledge or trait, not just, random stuff like they were distracted or a question was confusing.
So reliability is about hitting the same spot consistently, even if we're not totally sure yet it's the right spot.
Perfect analogy. Consistency. Let's dig into reliability a bit more. To really get it, we need this idea of a true score.
True score. Sounds theoretical.
It is. It's the score someone would get on a theoretically perfect test, one with absolutely zero measurement error. An ideal.
Right, not something we ever actually see.
No. What we see is the obtained score. And that obtained score is always influenced by measurement error. That's all the random, unpredictable stuff that affects the score.
Like having a bad day, misreading a question, maybe the room was too hot. Stuff's off.
Exactly. Random factors. So the classic idea is shown as x equals t plus e. Your obtained score, x, equals your true score, t, plus that error, e.
X equals T plus E. Obtained score is always a mix of true ability and random error.
Yep. And when we talk about reliability, we're essentially trying to figure out how much of that obtained score, x, is actually reflecting the true score and how much is just error, e.
Okay, but we can't see the true score or the error directly, so how do we figure out the reliability?
We have to estimate it. We look at how consistent the scores are under different conditions, like across time, or using different versions of the test, or even with different items within the same test.
So consistency is our clue.
It is. And we summarize this consistency using the reliability coefficient, often written as RXX or RI.
RXX, like correlating the test with itself somehow.
That's the idea. It's a correlation coefficient, ranges from 0 to +1. And the neat part is, you can interpret it directly. It tells you the proportion of variation in the obtained scores that's actually due to variation in the true scores.
Whoa. Okay. So if a test has a reliability of, say, 0.90, that means 90% of the differences we see in people's scores on that test are likely real differences in whatever the test is measuring, and only 10% is random error.
Yeah, that's exactly right. And generally, for most tests, we like to see reliability coefficients of 0.80 or higher. That's considered pretty decent.
Okay, 0.80 and up. But you said earlier, high reliability doesn't mean it's measuring the right thing, just that it's measuring something consistently.
Crucial point. Absolutely crucial. Reliability is necessary, but it doesn't guarantee validity. You need both.
Right. Okay, you mentioned there are 4 main ways to estimate this reliability coefficient. Let's start with the first one. Test-retest reliability.
Okay, retest is pretty intuitive. You give the exact same test to the same group of people at 2 different points in time.
And then you correlate the scores from time 1 and time 2.
Exactly. If the correlation is high, it suggests the scores are stable over that time period. This coefficient is sometimes called the coefficient of stability.
Makes sense for things that should be stable, like maybe personality traits or aptitude, but probably not great for, like, mood, which can change day to day.
Precisely.
Yeah.
Not good for fluctuating characteristics. Also, there's a potential problem if taking the test the first time changes how you do the second time.
Oh, like practice effects.
Yeah.
Or remembering answers.
Yeah. If it's a memory test, test-retest is probably not your best bet.
Okay. So what's the second method?
Alternate forms reliability, sometimes called parallel forms. Instead of the same test twice, you create 2 different versions of the test that are designed to be equivalent.
Equivalent how? Like same topics, same difficulty level.
Exactly. Same content, same difficulty, similar format. You give both forms to the same group, usually close together in time, and correlate the scores. This gives you a coefficient of equivalence.
Seems like making 2 truly equivalent forms would be really tough.
It's often the biggest challenge with this method, definitely. And like test-retest, it's generally better for stable traits.
Okay. Avoids the memory problem, but creating the forms is hard. What's the third approach? You said it only needs 1 administration.
Right. Internal consistency reliability. This looks at consistency within the test itself from just 1 testing session.
How does that work? Seems more practical.
It often is. One common way is the split-half method. You give the test, score it, and then you divide the test into 2 comparable halves.
Like odd-numbered questions versus even-numbered questions?
That's a common way, yeah.
Yeah.
Then you correlate the scores people got on the odd half with their scores on the even half.
Okay. The logic being, if the test is internally consistent, people who do well on one half should probably do well on the other half too.
That's the idea, but there's a catch. When you split the test in half.
Oh, right. You've made it shorter. And shorter tests are usually less reliable.
Exactly. So the split-half correlation actually underestimates the reliability of the full test.
Ah, so how do you fix that?
We use a correction formula, most commonly the Spearman-Brown prophecy formula. You don't need to memorize the math, but know that it adjusts the split-half correlation to estimate what the reliability would be for the full test length.
Okay, so Spearman-Brown corrects for the shortening. Got it. Are there other ways to get at internal consistency?
Yes. 2 other very common ones are Cronbach's coefficient alpha and the Cooter-Richardson formula 20, or KR20. These also only need 1 administration.
Cronbach's alpha, I've heard of that one.
Yeah, it's widely used. You can think of it conceptually as like the average of all possible split-half reliabilities, all corrected by Spearman-Brown. It gives a really good overall picture of how well the items hang together to measure the same thing.
Okay, the average of all possible splits. And KR20.
KR20 is basically a special case of Cronbach's alpha. It's used specifically when the test items are scored dichotomously, meaning right or wrong, yes or no, like multiple choice questions. Alpha can handle items with more response options, like Likert scales.
Got it. So internal consistency methods are good when the trait might fluctuate, or when practice effects are a worry.
Yes, because you only test once, but they have their own limitations.
Yeah.
They aren't great for speeded tests.
Speeded tests, like where the goal is to answer as many as possible in a short time, why aren't they good for those?
Well, think about it. On a speeded test, most people might answer, say, the first 30 questions correctly and then run out of time. Their responses to the items they answered will look very consistent internally, right?
Yeah, everyone got the same ones right because they didn't get to the harder one.
Exactly. So the internal consistency coefficient might look artificially high. even if the test isn't reliably measuring the underlying ability across its full range of difficulty.
Okay, that makes sense. So fourth method, inter-rater reliability.
Right. This one's crucial whenever the scoring involves some human judgment.
Like scoring essays or rating behaviors in an observation or interpreting projective tests.
Precisely. The scorer themselves can introduce error or inconsistency. So inter-rater reliability checks how consistent different judges or raters are when scoring the same responses or behaviors.
How do you check that? Have two people score the same thing and see if they agree?
Pretty much. You have multiple raters score the same set of tests independently, and then you correlate their scores or calculate an agreement statistic.
Are there specific stats for this?
Yep. For categorical ratings, like diagnostic categories, the kappa statistic is often used. It corrects for agreement that would happen just by chance. For rank data, there's the coefficient of concordance. The key is seeing how much the raters agree beyond chance.
Okay. Kappa for categories, concordance for ranks. Makes sense. So quick recap on that practice question. Why is internal consistency best for a characteristic that varies over time?
Because test-retest and alternate forms measure stability between two time points. If the thing itself changes, those methods will show low reliability. Internal consistency captures reliability at a single point in time, avoiding that problem.
Got it. Okay, now let's talk about the standard error of measurement, the SEM. You said it relates to the fact that scores aren't perfectly reliable.
Exactly. Since there's always some measurement error, any single obtained score is just an estimate of the person's true score. The SEM gives us an index of how much error we can expect in an individual score, on average.
So it's like the standard deviation of the errors.
That's a great way to think about it. Imagine someone could take the test an infinite number of times. Their scores would form a distribution. The mean of that distribution would be their true score, and the standard deviation of that distribution would be the SEM. It tells you about the typical spread of scores around the true score due to error.
Okay. And we estimate the SEM using the test's overall standard deviation and its reliability coefficient.
Correct. Higher reliability means lower SEM, less error. Lower reliability means higher SEM, more error.
And how does the SEM help us interpret scores? You mentioned confidence intervals.
Right. A confidence interval uses the SEM to create a range around the obtained score,
Yeah.
within which we can be reasonably confident the person's true score actually lies.
Reasonably confident, like 95% confident.
Yeah, that's a common one. For example, to create a 95% confidence interval, you typically take the obtained score and add and subtract about 2 standard errors of measurement. So if someone scored 50 and the SEM was 3,
Then 50 plus or minus 6. So the 95% confidence interval would be 44 to 56. We're 95% sure their true score is somewhere in that range.
exactly. It's a much more realistic way to think about a score than just taking the single number at face value. A 68% confidence interval would be roughly plus or minus 1s.
Okay, acknowledges the wobble in the score.
No.
Now, what things influence how reliable a test is in the first place? What makes that Rx coefficient go up or down?
Good question. 3 main factors we should cover. First, test length.
Longer tests are more reliable, right?
Generally, yes. All else being equal, adding more good items gives you a better sample of the domain, reducing the impact of error on the overall score. A 200-item test is usually more reliable than a similar 100-item test.
Makes sense. More data points. What's the second factor?
Examining heterogeneity. How diverse is the group taking the test?
Heterogeneity, meaning a wide range of scores.
Exactly. If your group has a wide spread of true scores on the trait being measured, the reliability coefficient tends to be higher. It's easier for the test to show consistent differences when the differences are large.
And if the group is very similar, like everyone's scores pretty close together.
That's called restricted range. If the range of scores is narrow, it actually makes the reliability coefficient look lower, sometimes artificially so.
Okay, so if an IQ test has a reliability of 0.90 for the general population, but you give it only to a group of people with IQs between 130 and 140.
The reliability calculated just for that group might be considerably lower, maybe 0.70 or something, because there's less variability for the test to work with. That's why sometimes you see reliability reported separately for different subgroups.
Important nuance. Okay, test length, group heterogeneity. What's the third factor?
The homogeneity of the test content.
Meaning, are all the items measuring pretty much the same thing?
Yeah. If a test is very focused, say 50 items all about classical conditioning, its internal consistency reliability is likely to be higher than a test with 50 items covering 5 completely different areas of psychology. More homogeneous content usually leads to higher internal consistency.
Okay, that makes sense too. If the questions are all related, the answers should be more consistent. So that practice question about the IQ test reliability being lower for gifted children, that's because of the restricted range.
Exactly. The gifted children represent a more homogeneous group in terms of IQ, leading to a restricted range of scores, which typically lowers the reliability coefficient compared to the general population.
Got it. Okay, that wraps up reliability pretty well. Let's switch gears to the other big one, validity. This is about accuracy, right? Measuring what you intend to measure.
Precisely. Does the test do the job it was designed for? Is it measuring the right construct? And there are three main types of validity evidence we usually talk about, often linked to why you're using the test.
Okay, what's the first type?
Content validity. This is most relevant when the purpose of the test is to assess mastery of a specific content area or skill domain.
Like achievement tests in school or job knowledge tests or that EPPP exam again.
Exactly. Content validity asks, do the items on the test adequately and accurately represent the entire domain they're supposed to cover?
And how do you establish that? Is it statistical?
Not primarily. It's mostly built in during test development. You carefully define the domain, break it down into key topics or skills, and then make sure you have a representative sample of items covering all those areas. The evaluation often relies on the judgment of subject matter experts.
So experts look at the test blueprint and the items and say, yep, this looks like a good sample of what a psychologist needs to know.
Pretty much. It's about rational analysis and expert consensus.
Okay, content validity is about covering the right stuff. What's the second type?
Construct validity. This is arguably the big one, especially in psychology. It's relevant whenever we're trying to measure a theoretical construct, something we can't directly see.
Like intelligence, anxiety, self-esteem, personality traits.
Exactly. Construct validity asks, does this test truly measure the underlying theoretical concept it's supposed to?
And how do you figure that out? Seems trickier than just looking at the content.
It is. It's an ongoing process of accumulating different kinds of evidence. It might involve expert judgment, seeing if groups known to differ on the construct actually score differently on the test.
Like comparing scores of clinically anxious people versus non-anxious people on an anxiety test?
Right. And a big part is looking at how scores on our test correlate with scores on other tests. We expect it to correlate highly with other measures of the same or similar constructs. That's convergent validity.
Okay, our anxiety test should correlate well with other anxiety tests.
And just as importantly, it should not correlate highly with measures of unrelated constructs that's divergent or discriminant validity.
So our anxiety test probably shouldn't correlate strongly with, say, a measure of artistic ability.
Exactly. If it does, we might worry it's measuring something broader, like general test-taking ability, rather than specifically anxiety. Now, one sophisticated way to look at both convergent and divergent evidence together is the multitrait-multimethod matrix.
Ooh, that sounds complex. Multitrait-multimethod.
It breaks down like this. You measure multiple different traits, like anxiety, depression, conscientiousness, using multiple different methods, like self-report questionnaires, observer ratings, maybe behavioral tasks. Then you correlate everything with everything.
Okay, why? What does that tell you?
The pattern of correlations helps you untangle how much of a score is due to the actual trait versus the method you use to measure it. Ideally, the trait should matter more than the method.
Ah, I see. You want the anxiety scores to be similar, whether it's self-report or observer rating, more similar than, say, anxiety self-report and depression self-report.
Precisely. There are 4 key correlations in the matrix. First, multitrait-multimethod.
Same trait, same method. That's just the reliability, right?
Exactly. Like correlating a self-report anxiety scale with itself, it sets the upper limit for validity.
Okay.
Second, monotrait-hetero method. Same trait, different methods.
Like correlating self-report anxiety with observer-rated anxiety.
Yes. You want this correlation to be high. That's your convergent validity evidence.
Got it. Convergent traits. Same trait, different method, high correlation.
Third, heterotrait-monomethod. Different traits, same method.
Like correlating self-report anxiety with self-report depression.
Right. You generally want this to be lower than your convergent validity correlations. If it's too high, it suggests your method, self-report, is creating overlap between supposedly different traits. This provides evidence for divergent validity.
Okay, divergent designed, different trait, same method, low correlation.
And finally, heterotrait-hetero method. Different traits, different methods.
Like self-report anxiety correlated with observer-rated depression.
Yep. You want this to be the lowest correlation of all, generally. Also supports divergent validity.
So the big picture, For good construct validity, the same trait, different method correlation should be high and definitely higher than the different trait correlations.
That's the essence of it. And that practice question about a large heterotrait-monomethod coefficient, why does that indicate poor discriminant validity?
Because if different traits measured by the same method are highly correlated, it means your test isn't doing a good job distinguishing between those traits, possibly because the method itself is introducing bias or overlap.
Perfect. Now, another tool for construct validity is factor analysis.
Right, you mentioned that earlier. It looks at how items group together.
Yeah, it's a set of statistical techniques used to identify underlying dimensions or factors within a set of variables or test items. If you have a theory that your construct has, say, 3 main components, factor analysis can help you see if the items you wrote for each component actually cluster together empirically.
So it checks if the internal structure of the test matches your theory of the construct.
Exactly. It provides evidence for both convergent validity, items measuring the same factor should load highly on it, and divergent validity. Items measuring different factors should load on different factors.
And those factor loadings are correlations between the item and the factor.
Yep. And squaring the loading tells you how much variance in the item is explained by the factor. There are also eigenvalues that help decide how many factors are meaningful. You can do it exploratory, just see what emerges, or confirmatory, testing a specific hypothesized structure. It's a powerful tool.
Okay, complex but powerful for construct validity. What's the third main type of validity?
Criterion-related validity. This one is all about prediction. It's relevant when you want to use a test score, the predictor, to estimate or predict someone's performance on some other outcome measure, the criterion.
Like using SAT scores to predict college GPA or a pre-employment test to predict job performance?
Exactly, those kinds of situations. And
Yeah.
ask, how accurately does the test predict the thing we actually care about? There are 2 subtypes here.
Okay.
First is predictive validity. This is when you measure the predictor now and the criterion later, like giving a test to job applicants, hiring them, and then measuring their job performance 6 months later.
So you see how well the test predicted future performance.
That's right. The second is concurrent validity. This is when you measure the predictor and the criterion at roughly the same time, like giving a diagnostic test for a learning disability and also collecting current teacher ratings of classroom difficulties.
Okay, estimating current status rather than predicting the future. And how do we measure this relationship?
Usually with a correlation coefficient called the criterion-related validity coefficient. It shows the strength of the association between the test X and the criterion Y.
And just like with reliability, we can square this Baraxi square to get the coefficient of determination.
Exactly. That tells you the proportion of variance in the criterion scores that can be predicted by the test scores. A validity coefficient of 0.5 means the test explains 25% of the variance in the criterion.
Okay. And if the validity is decent, you can use a regression equation to actually predict a criterion score from a test score.
Yes. And just like we have the EASE for reliability, we have the standard error of estimate here, which helps create confidence intervals around the predicted criterion score. Acknowledges that predictions aren't perfect.
Got it. Now, there was also this concept of incremental validity. What's that about?
Incremental validity asks a really practical question. Does using this test actually improve our decision-making accuracy compared to what we could do without it, or with just the information we already have?
So does it add value? Is it worth using?
Pretty much. We often visualize this using a scatter plot of predictor scores versus criterion scores. We set a predictor cutoff, for example, the minimum test score to hire someone, and a criterion cutoff, for example, what defines successful performance.
Okay, that divides the scatter plot into 4 boxes.
Right. You get true positives, predicted to succeed and did, false positives, predicted to succeed but failed, false negatives, predicted to fail but would have succeeded, and true negatives, predicted to fail and did.
Okay, the 4 outcomes.
To find incremental validity, you first figure out the base rate, what percentage of people succeed without using the test, for example, based on interviews alone. Then you figure out the positive hit rate using the test, what percentage of those who scored above your test cutoff actually succeeded.
So positive hit rate, true positives plus false positives.
Correct. The incremental validity is then the positive hit rate minus the base rate. It's the boost in prediction accuracy you get from adding the test.
So if the base rate success was 60% and using the test gives you a positive hit rate of 80%, the incremental validity is 20%.
Exactly. And whether that 20% boost is meaningful depends on the context, the costs of testing, and the costs of making wrong decisions. False positives versus false negatives.
Makes sense. That practice question asked what happens if you raise the predictor cutoff score.
Right. If you raise the cutoff, you become more selective. You'll hire fewer people overall. This generally means you'll have fewer true positives because you accept fewer people, but also fewer false positives because you're setting a higher bar. The impact on false negatives is that you'll likely have more of them, rejecting more potentially successful people.
It's a trade-off. Reducing bad hires might mean missing out on some good ones.
It's always a trade-off. Okay, last point. The relationship between reliability and validity. How do they connect?
Well, reliability is necessary for validity, but not sufficient. You can't have validity without reliability.
Perfect summary. A test simply cannot be more valid than it is reliable. Technically, the validity coefficient, Rxi, cannot exceed the square root of the reliability coefficient, Rxx.
So if reliability is 0.81, validity can't be higher than 0.90.
Correct. But remember, a test can be highly reliable, consistent, but still not valid if it's consistently measuring the wrong thing.
Like our scale consistently showing the wrong weight.
Yeah.
Reliable, but not valid for measuring actual weight.
Exactly. You need both for a test to be truly useful.
Wow, okay. That was a deep dive indeed. Yeah. So, boiling it down, when evaluating any psychological test, we really need to ask, one, is it consistent? That's reliability. And two, is it accurate? Is it measuring what it's supposed to? That's validity.
That's the core of it. Understanding those helps us judge if the information we get from tests is actually meaningful and useful. Can we trust the scores?
And these ideas, consistency and accuracy, they kind of apply beyond just formal tests, don't they? Like evaluating any claim or measurement we encounter.
Absolutely. It encourages a more critical way of thinking about information generally. How dependable is this source? Is it really measuring what it claims?
Yeah, good point. Well, hopefully this discussion sparks some interest. If specific things like the multitrait-multimethod matrix or factor analysis caught your ear, definitely worth exploring them more.
For sure. And thinking about tests you might have taken yourself, how might their reliability and validity have been checked? It makes it more concrete.
Definitely. So I guess a final thought is just that assessing these tools is never really done, is it? It's an ongoing process of gathering evidence and critically engaging with how we measure complex human traits.
Well said. Constant vigilance is needed to ensure our assessments are truly adequate and insightful.